Welcome to today's Oracle Machine Learning Office Hours feature highlight. Our topic today is Oracle Machine Learning for Python 1.0, the REST API for embedded Python execution on Autonomous Database, with our speaker, Sherry LaMonica. I'm your host, Mark Hornick. So in this session, we'll take a more in-depth look at OML4Py and its REST API for embedded execution on Autonomous Database. Sherry will provide an overview of the feature, its interfaces and usage, and then a demonstration. And with that, I will turn it over to Sherry to take us through OML4Py.
Okay, so let's get started. So today we'll be covering the Oracle Machine Learning for Python, or OML4Py REST API for embedded Python execution. And here's the agenda for today's session. First, we'll provide a quick overview of OML4Py embedded Python execution and the benefits and motivation for using it. Then we'll show you the different interfaces for embedded Python execution, including the REST API. We'll do a deeper dive into the REST API, show a typical workflow, a short demo, and then open the floor for the Q&A. Let's start with an introduction. Embedded Python execution refers to running Python functions which may contain third-party code in the database environment. And specifically, it's the ability to run Python functions and Python engines under the control of the database environment. And those Python engines can be spawned in a data or task parallel manner. The functions can be invoked directly from the Python interface, but also using the SQL interface or REST endpoints on Autonomous Database, and using a SQL interface with Oracle Database. Embedded Python execution works with the OML4Py data store, which is a repository in the database where Python objects can be saved and passed to user-defined functions, and also with the script repository, a database table that stores the user-defined Python functions that can be invoked from embedded Python execution. And you can retrieve structured or image results depending on your application's requirements, for example, a table, XML, PNG, or JSON. So why use embedded Python execution? It enhances OML4Py functionality by enabling users to run third-party packages and Python scripts in the database environment, and can potentially improve performance when running in a data or task-based parallel manner. It facilitates the use of Python scripts results in applications where you develop your Python scripts interactively with the Python interface and then invoke them from application-based SQL or REST interfaces. The Python scripts are securely stored in Oracle Database and can be scheduled to run automatically in SQL using the DBMS scheduler. And all of these features facilitate and streamline the collaboration among your data science teams, allowing the handoff of work from data scientists to application developers for deployment. So with embedded Python execution, users can score data at scale when using third-party code like scikit-learn when building a model, and then score chunks of data in parallel. They can automate building multiple models aggregated by a grouping variable in parallel, for example, grouping the data by color or gender. And you can build a model on those data partitions, save the results in the database, or access the results dynamically in applications or dashboards. And we can also conduct simulations by invoking a function multiple times in parallel. So now let's take a look at the interfaces for embedded Python execution. So you're going to use the Python interface to develop your functions and create reproducible and shareable scripts. And then you'll use the SQL and REST interfaces to deploy these scripts in applications. So the scenario is you would be developing and sharing your Python functions, including third-party code in the Python interface, and then you would leverage the parallelism and scalability of the database through embedded Python execution, either in Python or SQL. And then, depending on your application requirements, deploy those same functions using SQL or REST. With the SQL API, your scripts can be scheduled to run using the DBMS scheduler. And then the REST API allows you to deploy scripts in REST-based applications through HTTP. There's no client package requirements other than a REST client like curl or Postman to initiate the calls. And a couple of things to note, the REST API for embedded Python is available on Autonomous Database only. And right now we have a small number of third-party packages that we include with OML4Py in Autonomous Database, and third-party package installation will be available there later this year. So now let's look at the specific functions used for embedded Python execution. So if you look at the table here, we have the Python, SQL, and REST equivalents for embedded Python execution. DoEval and PyQEval will invoke a standalone script with no table input. TableApply and PyQTableEval invoke a script with table input, and RowApply, PyQRowEval will invoke the script on chunks of rows. GroupApply, PyQGroupEval, they invoke a script on a grouping column, and then IndexApply and PyQIndexEval run a script a specified number of times. And the functions in the last three rows, the row, group, and index-wise operations are all parallel enabled. Okay, let's take a closer look at the REST API. Here's the basic architecture for the OML4Py REST services. You'll use a REST client, like curl or Postman, to get an authorization token so that you can access all of the OML4Py REST endpoints. And to get the token, you need an Autonomous Database username and password, and the user needs to be granted the OML developer role by your Autonomous Database administrator. And I am mentioning this because there are some database users that may not have all of the grants for Oracle Machine Learning. You might have the grants for connecting to the database and running certain queries, but you do need the OML developer role for the OML capabilities. So after you have all of your roles and the token, this allows you to have access to the OML4Py REST services that are residing in your data center region. To get the token and run your REST API requests, you need the OML URLs that map to your tenancy and database. You can actually get these in your Autonomous Database in Database Actions under Related Services. You'll find two URLs, and there's one that is used to get the token. That's the token URL, and another URL to list and run the Python scripts. So you'll want to copy those and keep them handy. This is the structure of the OML REST URL for all of the REST endpoints. It has your tenancy ID, database name, your data center region, along with the root domain, which is oraclecloudapps.com. And for each database, the tenancy ID and the database and potentially the region will be different than what you're seeing here, but the root domain is the same for all of the OML URLs. These are all of the OML4Py REST endpoints and their methods. The administration components are for getting the authorization token. The generic components are there so you can view the open API specification. And then we can list and invoke the scripts that you have available to you, which are either scripts you've created or scripts that another database user has saved as global scripts. And again, GroupApply, RowApply, and IndexApply, they are all parallel enabled. The scripts can run in synchronous mode, which is the default, or asynchronous mode for any scripts that take longer than 60 seconds to complete. When you're using the asynchronous mode, there's the ability to pull the job status to see if it's still running. And then when it's finished, you can look up the job result according to a job ID that's provided. Before we get into the demo, I'm going to describe a typical workflow when using the OML4Py REST API so you can get a general idea on how this works. You'll start by writing your Python code and then create a function from that code. And a best practice is to ensure that the function works as you expect in Python prior to invoking it in embedded Python execution, and then run the function from the Python interface for embedded Python execution and fix any issues you might find in your code during those steps. And then at this point, you'll save the script to the script repository and run the function that is saved in the script repository from the Python interface for embedded Python as a named script. And once you know that's working, you can get a token and run the function from the REST API. So what does this look like in practice? Here we're building a model in Python with the name modRF. It builds a random forest model and saves the model to a data store using OML DS save, and the data store name is DS1. Then we define a scoring function predRF that loads the model from the data store and does the scoring, returning the predictions along with the original data. And as you can see, the function takes the data and the data store name as input. OML script create saves the function to the script repository, and we're using OML sync to get the proxy object, iris, and then invoke the function using row apply, specifying the script and data store names that we want it to run 50 rows at a time in parallel. This is the token request sent using curl. The items highlighted in green here will be provided by the user, the OML user name and password, and the OML URL corresponding to your database. And then you can see the token portion of the URL. That's the token endpoint, which is the same for all of the autonomous databases. And once this call is initiated, the token is returned, and it's valid for an hour and can be extended or refreshed before it expires. If you'd like, you can list the scripts that are available to you, which will be the scripts that you have saved to the script repository, and scripts that were saved as global scripts by other users in your database. And to do this, you'll send a GET request to the scripts endpoint, and you'll need to include your token with the request. To get the Open API description, you'll send a GET request to the PyScripts version 1 endpoint, and again, include your token with the request. And what this does is it returns all of the available endpoints along with their API descriptions. Okay, so now we're going to run the predrf function from the REST API. So we send a post request to the row apply endpoint. We specify the input table iris, the data store name DS1, that we want to score the data in parallel chunks of 50 rows using the medium service level, which corresponds to the level of parallelism that we want, and we include the token with our request. Autonomous Database offers parallelism through different service levels. The service levels are low, medium, and high, and they control the degree of parallelism for the jobs. Low has a maximum of 2 degrees of parallelism, medium has a maximum of 4, and high has a maximum of 8 degrees of parallelism. And specifying parallel equal to true in your REST calls corresponds to the service level. And the parallelism is applicable to row apply, group apply, and index apply. Okay, so let's move to the demo. Okay, so you are looking at OML notebooks. And this is a Zeppelin-based notebook interface, and I have a workflow here that is equivalent to the slides that we just saw. So we're going to create and save a function in the OML4Py script repository, authenticate the database user and get the token, and then run the saved user-defined function from REST using synchronous and asynchronous modes. So the first thing that we're going to do is load our libraries and create the iris data frame in this Python paragraph. So this is Python code. And then we're showing the first 6 lines of that iris data frame. And then we'll create the iris database table and proxy object using OML create. And then again, we're showing the first 6 rows of that proxy object, OML iris. So here is where we're building the model, the scikit-learn random forest model using random forest classifier. We build the model and fit it, and then you can check the importance of the features. But the important step is that we're actually saving the model to the data store using OML DS save. And we're saving it with the name modrf. The data store name that we're providing is DS1. We're overriding any data store with the same name if it exists, and then we're providing an optional description of that data store. And then you can view the contents of the data store using OML dsdir or OML dsdescribe. Both functions work to show you what summaries of what's inside the data store. And the reason, again, that we're saving the model to the data store is that our user-defined function is going to load that model and then do the scoring. And so here is our scoring function, predrf. And I'm creating a string that contains the definition of the scoring function and then saving it to the script repository using the OML script create function. The OML script create function contains two arguments, one for the function name and one for the script name. And you'll see that in a second. So here's our user-defined function. And what it's doing, it's using OML DS load to load the model object, and then it's doing the scoring, and then it's plotting the first tree. So in this case, our user-defined function is going to return both data and an image. And you can see what that looks like. So here we're storing the UDF in the script repository using OML script create. The function name is predrf, and I'm saving it as script predrf. I'm making it a global script so that other users in the database can run it if they want to, and overriding any script with the same name if it exists. And as a best practice, it's good to test the function that's saved in the script repository prior to running it from the REST API and the Python API for embedded Python execution. And we're doing that here with OML table apply. And so we're providing the script as a function as a name script and specifying the data store name. And then we set graphics equal to true because our user-defined function is returning both image and data. And there's the image and the data that's being returned from the Python API for embedded Python execution. And now you're ready to run the function from the REST API. So as I mentioned earlier, you first need to get a token. And first thing I should mention is that I have all of these curl commands in the notebook. They don't actually run in the notebook. This is for illustrative purposes only. You would be running this from curl or a REST client like Postman, but this is how you would run it if you were using curl. So what I've done here is I've exported my OML URL to a variable called OML server. And then my username and password, I've also exported those to variables. And then I send a post request to the token endpoint. And what comes back is my token right here inside these quotes. It's actually much longer than this. I've shortened it for the demo. But this token right here is what you need to authenticate for scripts that you want to run from the REST API. And it expires in an hour. And it can be refreshed before it expires. And here are a few examples of how you might run the predrf function from the REST API. So the first example here is running it with full table input, so no parallelism, in synchronous mode. And as you can see, I'm sending a post request to the table apply endpoint, and I have my function name there. My inputs are my table and my data store name. We have set graphics flag to true because the function returns image and data, and the autonomous database service level as low because table apply doesn't support parallelism. To run this data partitioned by rows in synchronous mode, I have to use the row apply endpoint, and then I specify the number of rows that I want per parallel engine. And here I specified 50 rows per parallel engine. And then I also specify the parallel flag is equal to true and the service level to medium for a medium level of parallelism. And if you have a longer running script, you can run in asynchronous mode. So again, we're using row apply here. The only thing that has changed is that I'm setting the async flag to true. It's false by default. So if you're running in synchronous mode, you don't have to specify that. But if you do want asynchronous mode, set async flag to true. And what's returned, you'll see here, is this job ID. So that's this string right here. And that job ID can be used for two things. You can use it to pull the job status, and you can use it to retrieve the result. So when you pull the job status, you're sending a GET request to the jobs endpoint and including that job ID. and you'll get one of two responses, either that the job is still running or you'll get this result URL. And then if you query that result URL, send a GET request to the jobs endpoint with your job ID and specify result, then you'll get your result back. And I also want to show you how this looks in Postman. So this is the Postman interface, and up here, I've specified an environment. So I have my OML server URL. That's my OML URL is already configured in here, and my username and password. So they're configured as variables. And this over here is called a Postman collection. And each item in the collection is its own request. So the first thing that we need to do is get the token. And you can see I have the token endpoint in my post request. And if you go over here, you can see that I'm actually saving that to a token. So you don't have to do anything after that. You just run this, and the token that comes back is saved to a variable for all of your remaining requests. So the access token is here, and it tells you that it's a bearer token, and it expires in an hour. And now if I want to check the Open API specification, I'm sending a GET request to the PyScripts v1 endpoint, and I just hit send. And you can see that the API descriptions are returned for you to look at. To list my available Python scripts, I am sending a GET request to the scripts endpoint. And what you get back here, again, are all of the scripts that you've saved to the script repository or that other users in the database have shared as global scripts. So it comes back in these JSON strings that you can, key value pairs. And then, but if you go over here, Postman does allow you to do some formatting of the results that come back. So you can also configure this so that you can view everything in tabular format. So we have the owner of the script, when the script was registered or saved, the name of the script, a description if it was supplied at the time that the script was saved, and then the script definition. And then finally, we are going to run the scoring function. The row apply endpoint, we provide our function name, predrf, and inside the body here, or where the request body is where we put all of our parameters. So we have the table name, the data store name, the number of rows that we want to run in parallel at a time, the parallel flag and service level, and then the graphics flag is set to true. And when this comes back, the data set has 150 rows, so you'll get the three chunks that come back, and each one will have the PNG image bytes and the data. So you have zero results, 0. So you can see these are the PNG image bytes. This is the data that's returned, and we have 3 chunks, 0, 1, and 2. In the slides here, I have some resources that you can look up. The Oracle Machine Learning webpage, the blog, our GitHub repository. It has OML4Py collections that you can run scripts, and also some curl examples, and then the OML office hours and OML4Py documentation. So let's open up the floor for Q&A. Any questions?
Yeah, actually, Sherry, we do have a few. The first one is the REST API available on ADW with a private endpoint? And how would the API URL change? Is this also available using the private endpoint?
Yes, it is available using the private endpoint. And I don't know how the URL would change. It ends up being configured by the administrator. So the URL has a different structure, but it still has the data center region, but the name of the private endpoint is in there.
And a second question is, how does OML4Py differ from OML4R or OML4SQL in the OML side? Besides the syntax inherent to the language, does it do the same thing under the hood?
Yeah, the architecture is the same between OML4Py and OML4R. And so there is an OML4R REST API. You can look up that presentation that we did in October, but OML4R also has embedded execution and the ability to run third-party code in parallel through R, SQL, and REST. In OML4R and OML4Py, we have in-database interfaces to in-database functionality, including 30 or so algorithms that you can run in the database, but you're actually initiating them from your R code.
All right, thank you. And another question came in to the Python UDF execution. How's the code executed in Oracle database? Do we use any API invoked from Oracle database itself, which internally executes the Python code, or directly the Python code is executed by the database using our customer Python interpreter?
Are we talking about the spawned Python engines?
Well, that's how I'm taking it. I think that the key thing, right, go ahead as far as, where it's actually processing this.
Yeah, so these are actually spawned in Python engines that are spawned and managed by the database. And on the OML4R side, then it would be R engines that are spawned and managed by the database.
Yeah, and there's actually a difference, right, between how we approach that with autonomous databases, Sherry was showing here, and on premises. So on premises, we're using our external process mechanism to enable that. And in the autonomous database, we actually have separate VMs from the database where these engines are actually being spawned.
Yeah, in the on-premises case, the database is still managing those extract processes. There's nothing additional that the user needs to do beyond what we've shown here.
Sherry, thank you very much for a very informative session, as well as great demos. And we look forward to seeing everyone at our next office hours.
Yeah, thank you for joining.